Mhm. So today we're gonna be talking about the real numbers. So this is what our class, so if our class was a play, you would have the characters, you know, and the real numbers are the players here, all right? So it is really about the real numbers. So to talk about the real numbers, maybe we should go back and talk about numbers before them. So the real numbers is what this is about. And it's 1.1. And before that, let's talk about the numbers in general. So what are the numbers that we know and use? Well, of course, the first set of numbers that one encounters on life is the natural numbers, right? We use this symbol to denote it. It's like a blackboard letter N. And these are the numbers we use to uh, to count, right? We associate them to a certain number of objects, and those are the numbers that you first learn. Um, Even babies can learn pretty early on the difference between 1 and 2. 1 when they're by themselves, and 2 when their mom is with them, and so on. From there on, it progresses. And we're not going to have a axiomatic approach to doing all of these, right? That would be kind of boring. So but there is a way. I have to mention this to you. So there is a way to start with some axioms, you know, like called the piano axioms, and using those, construct the natural numbers. Say specifically what is the meaning of 1 and what is the meaning of 2 and why 1 plus 2 equals 3 once you define properly the operation of addition. But we're not going to do that. So I'm going to assume you know these natural numbers, and you know that those are the ones you use to count things, and that you also know how to operate on them, right? You know how to add them and multiply them. And once you have those operations, pretty soon you realize that you're kind of restricted. So for instance, um, if I go back to elementary school, you will have this time of fill the blank problems, right? Where it's like blank plus 3 equals 5, right? A problem like this. Oh, well, that's easy, right? And we'll look for the answer, and the answer is the number 2, right? Because 2 plus 3 equals 5. But then, if you switch those numbers around, if I put the 5 here and the 3 here, and then I ask what is the answer here, suddenly I can't really answer this question, right? Because there is not a number that, one of these, there is not a natural number that when added to 5 gives me 3. And that's a problem. So the way to solve this is to actually extend these numbers, right? And you can extend them precisely by adding the solutions to this type of equations, right? So in a more advanced setting, what we're really doing is trying to solve this equation, right? X plus 5 equals 3. What is X? And we cannot, there is no solution if we restrict ourselves to the set of natural numbers, but there is if we extend ourselves to the integers. And the integers, we use this blackboard letter C, and it consists of 0 and the natural numbers, as well as -1, -2, etc. All the negatives of the natural numbers. A little note here, by the way, it's we mathematicians do not agree whether 0 should be a natural number or not, right? Some books have 0 as a natural number, some others don't. Our book doesn't, right? And it's just a convention, really. You gain nothing one way or the other. I personally like 0 to be a natural number. That's my own opinion, but the book doesn't. So I'm going to conform to what the book has and just start the natural numbers at 1, right? Okay, so these are the integers. Then after the integers, if we also use the other operation, multiplication, then again, you quickly realize that there are questions you cannot answer, these type of blank questions. If I have the equation 2x equals 6, and I ask what is the x that makes this true, then we know that x equals 3 works. But if you tell me 2x equals 5, suddenly none of these guys work, right? There is not an integer that multiplied by 2 gives you 5, because that would mean 5 would be an even number, and it's not. We know that, right? So the way to fix this is, again, to enlarge our set, and that is how we come up with the set of rational numbers. We know we use the blackboard letter Q, and this is defined as the numbers a over b, such that a and b are integers and b is not 0, right? We can't divide by 0. By the way, if you've never wondered, many of you, I bet you already know, why the letter Z, right? When I was an undergraduate, that kind of question bugged me for some time. Why the letter Z here? It makes no sense. The N makes sense, natural. The Q makes sense because they're like quotients, right? Quotients of integers. The Z never really made sense until I found out why. And the reason why is because it comes from the German, right? It's the German word for number, Zahlen, starts with the letter Z. So that's where the mysterious Z comes from. A little bit of trivial information for you. Okay, the rational numbers. Now, the rational numbers are great in the following sense. If you add the operations addition and multiplication, this guy is a field. Now, what is the meaning of being a field? Well, if you already taken 360, you know what I'm talking about here. If you haven't, no biggie. It just means that this set with these operations satisfies a bunch of nice properties, the type of properties that you like. For example, that if you take two A and B and you add them, that's the same as B plus A, right? You can call that the commutative property for addition. If you do A plus and then you add B plus C, well, you can first do A and B and then add C, and that's fine. That's the associative property, right? There's a special number called 0, and if you add 0 to A, you get the same. For every A, there's another guy which is it's negative, and when you add them together, you get 0. That's also awesome, right? These together tell you that Q with addition is an abelian group. If you don't know what I'm talking there, don't worry. Similar things happen for multiplication. So A times B is the same as B times A. A times B times C is the same as A times B, and then times C. There's a number called 1, and when you multiply it, you get the same. And there's an inverse, and when you multiply them, you get 1. This happens for every A that is not 0. And also, there's two properties that combine these two together, right? If you do A times B plus C, the so-called distributive property, then this happens, and you can also do it with addition first, right? So all of these nice properties hold, and all of these properties tell you that the rational numbers are a field, right? And in 360, we actually take a lot of time to study fields in general, and we look at other fields that are not necessarily this one, and fields that have these nice properties as well. Now, the rational numbers actually have another nice property, which is they're not only a field, they are an order field. So Q is a totally ordered, that's a more correct term, field. And what do I mean by that? Well, I mean the following. I mean, if you have two rational numbers, then you can compare them. One of these three things should happen. Either R is less than S, or R is equal than S, or R is greater than S. That's awesome, right? So we get to compare any two numbers, and we can tell which one is bigger. So, I mean, sometimes not in an easy way, but we should be able to tell which one is bigger. the rational numbers are so awesome that for the purposes of everyday life, pretty much those are the only numbers we use. So people on the street, regular people, when you talk about numbers, these are the numbers that they probably are using all the time. They don't even care to work with the ones that are not rational. So anything that has to do with measurements, you probably only use rational numbers. So money or weight or quantity of an object that you're buying, anything like that will be a rational number. And that's why it was surprising for the ancient Greeks when they discovered that these were not all the numbers, right? So for a while, the Greeks thought that maybe the rational numbers were all the numbers that you needed. And they discovered that these are not all of the numbers, okay? And we'll talk about that. But first, let me tell you another nice property of the rational numbers, right? If you represent them on the line, right? For example, let's say that 0 is here and 1 is here and then 2 and 3, then between 2 and 3 is exactly 5/2, right? That's a rational number. And somewhere over here is 1.23. Right? That's another rational number, right? Any number that you can write as a terminating decimal is a rational number, correct? Like 1.23. Why is this guy a rational number? How can I tell? Well, I need to write it as a fraction of two integers, right? What would be the two integers?
123 over 100.
Good. Yes, thank you. Right? And it works, even if it's not simplified. In this case, I think it is. But even if it wasn't in simplified form, that's it. That's a quotient of two integers, right? So which makes this a rational number. It belongs to the rational numbers. We'll talk more about what this terminology means very soon. So we can represent rational numbers on this line, and a beautiful property that the rational numbers have is the following. If you have two rational numbers, where it doesn't matter where they are. So if I pick a number over here, R, and another one here, S, well, no matter what R and S are, you can find another rational number. There is always a rational number between R and S. Can you tell me one? Which one would work? No matter what R and S are. So
R plus S over 2.
Yeah, that one works, right? So for example, R plus S over 2.
Would we need to specify that R and S are not equal?
Yes. Yes. Let's. Absolutely, right? Otherwise, what does it mean in between? Yeah, so there's that one over there. So how about another one? Is there only one?
R plus S over 3.
R plus S over 3 may not be there, right? R plus S over 3. That's a good guess, but may not be between R and S. Let me think of a specific number that would make this fail. Let me think. What if we make R0? No, R0 was going to work. Let's see which ones.
Would that be R equals 1 and S equal to 2?
For example, right? Or anything less, like R equals 1 and S equals 1.5. Let's do it like that, right? So then R plus S would be 2.5 over 3, which is less than 1, right? Yeah? So that one doesn't really work. But you can, see, here's one you can do, of course. You can just repeat the previous trick we did. So we had R and S. Let me do another picture. So you did R and S, and you can do the midpoint of this. And then to find another one, how about doing the average of these two, right? The average of R and R plus S over 2. So that's going to be R plus R plus S over 2 over 2, which is a number that we like to call 3R plus S over 4. So that one works. And this one over here is actually R plus 3S over 4. That one works too. So there's not only one rational number in between any two, there's a lot of them, right? If you continue with this, you can quickly convince yourself that in fact there are infinitely many rational numbers. So it means like the rational numbers are all over the place. So in this real line, they are all over the place. And that's what I was telling you, that for a while, the people thought that you could, every rational number, I mean, all the numbers in this line were rational, that all the numbers in this line would work. And it's not true, okay? And that's our first little result here. So this is theorem 1.1. And it says the following. It says, there is no rational number whose square equals 2. All right? And why is that? And this is, by the way, when the Greeks discovered this, they thought it was such a big deal that they sort of wanted to keep that information hidden, right? They were only, you had to be a member of the Pythagorean club to really be able to gain this knowledge, right? They thought like, wow, this is heavy. I mean, this is something that we weren't anticipating, so a type of knowledge that we shouldn't share so easily. Essentially, what this is telling you is that the number square root of 2, right? Because we know there is, see, okay, let me tell you about that. How is this related to the Pythagorean theorem? Well, the idea is that if you take a look at a square, so the Pythagoreans obviously knew the Pythagorean theorem. So they knew that if you have a square, right, and the length of this square is 1, you could maybe be interested in how long is the diagonal. And that definitely comes from the real world, right? Like, how long is the length of this diagonal? And if we didn't know it, if we call it x, and we knew the Pythagorean theorem, which they did, they even proved it and everything, then you would know that the Pythagorean theorem tells you that 1 square plus 1 square equals x squared. In other words, 2 equals x squared. So the length of the diagonal is a number that when you square it, you get 2, right? So that's exactly the number we're talking about here, is that number whose square equals 2, is the diagonal, the measurement of this diagonal. So in modern terms, x is the square root of 2, okay? So why is this number not a rational number? And it's one of those proofs that you should have seen in Math 320. I mean, well, we'll repeat it here regardless. So why is this true? Well, and it's a proof by contradiction, right? So you suppose that it is a rational number. So suppose there is a rational number P over Q such that P over Q squared equals 2, right? And because a rational number you can always write down in simplified form so that you don't have common factors here, you can cancel them. Let's assume that's the case. So assume P and Q have No common factors. Okay, then this is what happens from this little equation over here. If we multiply by q squared, what we get is that p squared equals 2q squared, right? And from here, the first thing we learn is that this number p must be even, right? Because if you have an odd number, if p were odd, then when you square it, when you multiply two odd numbers, you get an odd number. But this guy is not odd, it's even, because you can see the 2, right? It's 2 times something. So I'll write that here. Note that 2q squared is even. So p squared is even as well. And hence, p itself is even. And the reason for that is the product of two odd numbers is odd. I mean, I'm trying to explain it in the simplest possible way, so only using even and odd numbers. If you know congruences, modules, all of that, then this can be written in an even easier way. All right? But that's what we know. So p has to be even. And what is the meaning of a number being even? Well, the meaning of a number being even is that p, we can write it as 2 times something. So let's call it 2 times capital P, right? Where capital P is an integer. Okay, and then I'm gonna write down my newfound information back to my original equation. And this is what happens. I get 2 times P squared equals 2 times Q squared. And if we expand this means 4 times capital P squared equals 2Q squared. And then if I divide by 2, what I get is 2 times capital P squared equals Q squared. And the funny thing here is that now this looks almost like that one, only now I have capital P and Q instead of little q and P, right? And but the conclusion is the same. The guy on the left is even, so then Q must be even. Again, we conclude that Q squared is even, and so Q itself is even as well. Okay, and that doesn't sit well with us, right? Because now what happens? Well, now both P and Q are even. But if both P and Q are even, then that means they have a common factor. And remember that we started without common factors right here. We said, assume they have no common factors. And they're both even now, so something is wrong, right? So we got a contradiction. And let's write it down. This is a contradiction because now both P and Q have a common factor 2. So a contradiction to what? Well, the only thing we supposed, right here on top, we supposed that there was a rational number that made this happen, and there isn't. So if we got a contradiction, that means our supposition was wrong. Hence, there is no rational number whose square equals 2. And that's the end of our proof. This is the first little proof that we do here in class. Of course, you probably were already familiar with this proof, but it was a big thing, right? I mean, there are numbers that are not rational numbers, right? And the numbers that are not rational numbers, then we call them irrational numbers, right? And you already know that together the rational numbers and the irrational numbers make up the real numbers, right? So informally speaking, if we talk about the points on the line, all of the points in the line, we call those the real numbers, right? And we know that there are some that are rationals, like the ones we talked about already. But we just discovered one that is not. This number, square root of 2, right? 1.41 something, it's more or less over here. Square root of 2. That guy is not rational, right? And there are other ones, right? There are many more. Pi, for example, the circumference of a circle of diameter 2, that is also not a rational number, right? And there's many, many more. In fact, it's kind of hard because when I ask you guys for irrational numbers, you're going to run out of numbers pretty quickly. So you're going to tell me square root of 2 and pi and e and maybe another square root of something, and then you won't have any more answers. But in fact, the irrational numbers are way, way more than the rational numbers. Okay, we'll get a chance to talk about that later on. What do I mean by way more? But they are. So there's lots and lots of irrational numbers. Okay, so this, like I was telling you, this section 1.1 was meant to be an introduction. And what I want to talk to you about, what we're going to be discussing is what is really the property of the real numbers that make them the real numbers. That's what we want to know. Okay, so what property does the real numbers have that makes them different from, say, the rationals? That's really the key aspect that we want to discover, right? And we're not gonna do that today, but this is where we're heading. What really makes the real numbers the real numbers? We need to understand that very well, because calculus, what really calculus is the study of functions of real variable, right? And if we don't even understand what the variables are, what the real numbers are, then it's going to be really hard for us to understand all these other ideas of calculus. So we need to start with the very basic notion of what makes them the real numbers. How are the real numbers different from the rational numbers? Okay, so for the next 5 minutes or so, I wanted to touch on some of the concepts. Or maybe I'll go back to the book and show you, because this is stuff you know already. So let's just quickly go through it. So the basic things that we're gonna need. Some preliminaries is what it's called, and it's mainly notation, how we're gonna write things. Okay, so we're gonna start with sets. And what we call a set is just a collection of objects, right? And the object either belongs or does not belong to the set. And we use this symbol right here. Maybe I'll go back to the page because it's a lot of writing that I don't want you to read from the screen. So let me go back to my page. So let's talk about sets. How do we write sets? So usually we use capital letters to denote them. So a set is intuitively a collection of objects. Like I told you before, we're not hoping to be very precise about the way we define sets. That's why I'm calling it intuitively, because this is not a precise definition. I could get in trouble. And in our case, they will be most often real numbers. So we seldom will have sets of anything other than real numbers. And if you call a set A and an element X, then when you write X belongs to A, that's what this symbol is. It means belong. What it really, this means X belongs to A. And you either belong or don't belong. It's not like, there's no such a thing like you belong 20% or 30%. No. Set theory is belonging or not belonging, all or nothing. Then we have some other operations. If we have two sets, we can look at things like the union. And the union is easy, is just put all the elements together, right? Take all the x's that are either in A or in B. And if they belong to both, fine, just include them, right? This is the union. This is the union of A and B. And we also have the intersection. And these are the elements that belong to A and B, that belong to both. Okay, so like I said, very, very basic. See that maybe we'll illustrate before we stop for today and do our quiz. Let me see if I can illustrate. So, yeah, so a little example here to illustrate this. So let's say that E is the set of even numbers, even natural numbers. So this is 2, 4, 6, 8, 10, etc. Right? So then what would be the set E intersection the set 1, 2, 3, 4, 5? Well, these are meant, yeah,
2, 4.
Yeah, so it's supposed to be the elements that belong to both, right? And in this case, there's only 2 and 4. So this is the set that has 2 and 4. By the way, because sets are the only thing that matters is the property of belonging. You can write 2, 4, or you can write 4, 2. It doesn't matter, right? It's not the order in which we list the elements is irrelevant. Both 2 and 4 are members of the set. Okay, that's important. All right, so we'll continue talking about these preliminaries next time. So at this point, you can go to Canvas and work on the quiz. Okay, I'll stay on the Zoom session in case you have any question, but go ahead and do our quiz.